So, you know what we're going to do today, we're just going to do a lot of problems. But I've got a million of these things. The floor is always yours first, so if you all have come across something that you can see, just let me know. Or if there's anything that I do that inspires another questions. So let's start off here. These are the latest grade problems. That's kind of the theme of today. So first problem, an airplane flies at a constant altitude. Three miles. And constant speed of 300 miles per hour. If the plane passes directly over a tracking station on the ground, how fast is the distance between the plane and the station, changing 48 seconds later? The plane travels directly over the tracking station. How fast is the distance? Plane station. Thing. 46. First thing to do with any of these things is you draw a picture, and this is not so that you can win an art contest. It's actually a tool to help you out, right? So what do we know? Well, here's the ground. Here's the tracking station. What do we know about the plane? It flies at a constant altitude of 3 miles. Here goes the plane. By the way, you have to put something about your label. Right, because what just that 3 miles changes, the problem goes on. No, it doesn't. The plane is always at 3 miles, constant altitude 3 miles. Right. So this distance right here in miles is 3. Right. It flies at a constant speed of 300 miles an hour. The plane travels directly over the tracking station. How fast is the distance between the plane and the station changing? Okay, well. One point, plane flies directly over the station. And then it keeps doing its thing, right? What else should perhaps I be drawing on this thing to help me out? What is it that I need to know? What okay, but let me get down to something more basic. There's a question asked about, there's something about the distance between the plane and the station. Right, so I'll probably need, I need to draw something between the plane and the station. And as I go along, let's call this something. Let's call this, I don't know, S. And let's call this X, right? It's always better to overlay them. I think I've kind of captured the essence of most of what I want. Let's see. Airplane flies at constant altitude of 3 miles. I've got that covered. constant speed of 300 miles an hour. So I interpret that one. Very good. The 300 miles per hour, what's changing? Right, what does that signify? That's the plane cruising, right? Right, that's X changing at 300 miles per hour. Right, okay. Okay, so I've got that piece of information. Plane travels directly over a tracking station, got that recorded. How fast is the distance between the plane and the station? But, so. What is our quest? What are we trying to find? Agreed. That is what we seek. When? Right. Uh, he is 48 seconds after plane is directly overhead. Maybe I need to reinterpret that. Well, let's see what happens. I think I might have to come back to this a little bit. Okay, before we get started, and this is actually, I think, important. But any class like this, you take, and if you all are the engineers, your sciences, etc., you need to know what your answer is. Can somebody tell me what you expect about this answer? DST, you expect that to be positive or negative? I expect it to be positive, because that S is growing, moved out that S is good down. Ballpark and figure. Well, so let me put it this way. The plane's 3 miles off the ground, right? If the plane were flat on the ground, right, that would be a stupid plane, but if it were flat on the ground, the DSTT would be 300, so that's how fast it's going. It's up in the sky 3 miles. Do you expect that DSTT to be more or less than 300 miles an hour? I think it might be less, right? Because if the plane were right level, it does 300 miles an hour. Here, the 300 miles an hour, it takes longer. I think it's going to be less. See what happens. We've got everything that we need from the problem right now. This is called related rates. So what we need, we know something about the STT. We want to find the STT. So we need an equation that balances X and S. Can anybody see an equation? That's right. That's exactly right. This is a right triangle. And so this sounds like a job for Pythagoras, right? So S squared is equal to X squared plus 9. Right, okay? I've done everything I can. This is really, ironically, calculus class. This is really the only calculus step. But we actually take the derivative. S is a function of time. As time goes on, S changes. X is a function of time. Take the derivative with respect to time, and I get 2S. And don't forget the STT. It's 2 blob to the first times the derivative blob. And I get 2X. Yes. Any questions? What is it that I see? I see that the STT. This is easy enough for me to solve for, so I'll go ahead and do it. So to fill this in, to answer our question, I need to know what X is. I need to know what DXT is. I need to know what S is. Well, I've got DXT. But I need to know S and X. This one I know. How can I find S and X? Make this work. Anybody tell me how I can find X? Finding it should be fairly easy, right? It's how far the plane has traveled in 48 seconds, right? And I know exactly how fast it's 300 miles an hour. The only pain in the butt is the fact that I've got 48 seconds, and you can convert that to hours. So 48 seconds. You all ever done unit conversion? Right, so this 1 second, well, actually, let me do it this way. One minute of 60 seconds and 1 hour, 60 minutes. Minutes cancel, seconds cancel. So this will give it to me in terms of hours. That's going to be what? So, and so X is 300 miles per hour. 1/75 hours, which is 4 miles. I also need to find S. How do I find S? Have this equation here, so. Yeah. So let's finish this off here. Yes, P is X, which is 4. The X which is 300 miles per hour. And S is 5. So basically it boils down to 4/5 of 300 miles an hour, 200. Okay, any questions? Here's a, here's one that you'll see in almost every calculus book ever written. A 13-foot ladder rests it begins slide down the wall. Well, actually, the base is the slide. Away from the wall. At 2 feet per second. Right, how many of you have seen something like that? You know, you've got something leaned up against the wall that slides down like a Chevron work. I try to lean this up against this thing, not a perfect model, but I can slide it down. So you all see what's happening in real life, right? So the base begins to slide away from the wall at 2 feet per second. How fast? Top of the ladder sliding down the wall. When the bottom of the ladder is 5 feet. Okay, so this is a problem about a ladder slide. You get a ladder leaning up against the wall, and somebody greased up the floor, so it started to slide. The bottom always slides at 2 feet per second. How fast is the top of the ladder sliding down the wall? The bottom of the ladder is 5 feet from the wall. Well, always, we're all picturing this. Got a vertical wall. Here's our floor. And here is a beautiful rendition of that. Okay, folks. Help me label it. How should I label this? Is it always? No, it's not always. That's actually, I'm glad you brought that up. You gotta be careful. If there's quantity in the problem that changes, it's a problem, or could change. It's a problem evolves, always go with the letters over the numbers. If you put a letter in where it should be a number, that's gonna be a deal. Put a number in where it's supposed to be a letter, that'll burn you. So maybe, but you're right, we should label this. It changes, it's probably on what should we call it? Let's call it X. What else changes? Yeah. This, that's a good thing to label. What else might be labeled here? The 13. This for sure does not change. It's always 13 feet long. Agree? Now, let's see. 13-foot ladder. Got that taken care of. Begins to slide away from the wall at 2 feet per second. Can somebody interpret that for me? Good. Is 2 feet per second. Okay. Okay, so that's kind of it. What's being asked of us? When what? Okay. I know the XTC. All the kinds of stuff about life. Maybe I need to play, probably answer that. So on. X squared plus Y squared is 13 squared. Now at this point, by the way, what do you expect about the answer to? You like to, you expect us to get a negative answer or a positive answer? I expect to get a negative answer, right? Because when that ladder slides down the wall, your X is getting bigger, but what's happening to your Y? Getting smaller. I expect to get a negative answer. Super happy. X. Y. This is similar to the previous one because I'm looking for what, like, so I can solve it. X. Solve that. Okay, so what do I need to finish this off? I need values. I need value for X, I need value for Y, I need value for X. Looks like I've got the X and T, no problem. And I've got X, that's part of the problem. I seem to be missing Y though. That's right. Again, go back to this well, here, this equation that governs everything. Next equals 5, I get 25. Y squared, 169. So I get Y. So, using this information here, I'm going to provide T negative. X is 5. The X and T was 2. Y was 12. That's minus 5. 6. So, and this is probably the right answer. This model is flawed. Anybody ever really seen ladders sliding down the wall? Anybody, so this is what we got. Right. So like, only one, physically speaking, this model probably works at the beginning of the problem, but can't always work. So that's essentially it. As the ladder gets closer and closer to the floor, it's closer and closer to the end. What is Y getting very close to? Y is getting very close to 0. What's X getting close to? Getting very close to 13. So here we've got 13 about, the X and T is always 2. So the numerator is getting close to negative 26. The denominator is going to 0. Great. So the Y and T is going to infinity. So at some point, the top of that ladder is faster than the speed of light, right? Which is constant. Has anybody ever seen something? I don't know how well this report down. I should have been here. Notice the top of that chair is falling. It's sort of at the end of the close to the floor. Got it. So here's an extra question. This can't be true because at some point this is going to speak light. See if you can figure out, give me a good argument for when the top of the ladder must come off the wall. So that chair, it's got to, as it slides down the top of the ladder, can at some point no longer be in contact with the wall. Figure out when that is. And actually, the key word that you said was acceleration. See, that might help. So think about that for fun. Okay, any questions? Okay, so this one's. Here's another one. A car. Take off. Starts. Sure. Oh, well, so for example, I mean, depending on, so if you throw this pin up in the air, the acceleration is always down, but the velocity is positive this way, negative this way, or depending on which way you do it, it's negative the other way. So notice that your velocity going up, and coming down, they change sign. Acceleration is always this. With a what?
Like a circle. Like one of these written out columns, but without circle.
Oh, yeah, we'll run across several of these. Two cars start the same. The first one goes 40 miles an hour. Exactly northeast. An hour later, the second car goes 50 miles per hour east. How fast is the distance between things? 2 hours after second car starts. So let's see what's going on. This one's a good example of one where I think the picture really does want to be a single tool. So one car starts off, they start off, say, New York. One car goes northeast like that. And the other car starts later, goes directly like that. So let's label these. Let's call this X for the first car, Y for the second. And let's label the distance between them. Call this S. By the way, is there anything else that I'm not explaining? What's changing in this? Why is changing makes a change? But their angle is gonna change. In fact, what is the angle? In the past, the next one. But it's 45 degree, I'm gonna call that I-4. Now, let's see here, two cars start the same point, got that. First one goes 40 miles an hour, northeast. So the picture's got the northeast picture. 40 miles an hour, what's that? An hour later, the second car goes 50 miles an hour. What do we see? And what? Part two has been driving for 2 hours. So what should Y be? Right, so Y is car two. And it's been going, what? 2 hours? 50 miles an hour, so what should Y be? 100. And what about X? I think I've got everything I can get out of that. So I need an equation. I know some stuff about the X, the T, Y, so I need an equation. The balances. Any ideas? So, thinking, right, this isn't what I think necessary. So, by the way, I'll give you this. Does anybody remember what the law cosine is? Remember seeing it somewhere? That's essentially. Because actually, it doesn't matter whether the angle is obtuse or not. A lot of cosines. Yes. You've got. Oh, same. Okay. Maybe you've seen that at some point, maybe you remember, but seen it at some point. Right. Notice if theta, does anybody remember what the cosine of pi over 2 is? It's cosine of 90-degree angle. It's 0. Because if this angle is 90 degrees, this turns into Pythagoras system, right? Because cosine of theta is 0. So this is just a general statement. Pythagoras system. So let's do that. Let's apply that. This will be supplied to you free of charge. cosine of power four is actually one over that. So here I get the equation. S squared is x squared plus y squared minus radical two. And there you go. There's the equation you want, balances x, y, and x. So let's take the derivative of this. This is two s dx t equals two x dx t plus two y t minus radical two x y t minus radical two y dx. Now, yes. Square root of two. It's basically two times one over radical two. For some power four, it's radical two. Now, let me take a bit back to assess here. So I've got the x and t, I've got the y and t, I've got x, I've got y, right? Here's y, x, got these, I've got these in space, no problem. But I'm missing something. What am I missing? Solve this equation, figure out what the s and t is, I need an s. And I've got x, y, x and t, y and t, I need to find s. Well, use this equation. X was what? 120. Y was 100. And X, oh, here we go again. X and Y, I guess it's 12,000. So I get, this comes to like 14,400, another 10,000, it's 24,400 minus 12,000. Radical two. That's what S squared is. So S is square root of this 4,000. And you know what? Until the last minute, I'm just gonna call this S, because nobody wants to write that crap every time, so I need to just write a little S. So let's do that. So the S and T is two X S T plus two Y T minus radical two X Y T minus radical two Y S T over two S. And actually, here's the truth of the matter. If you're hurrying on the test or something like this, remember, I don't really care that much these calculators, but I don't care what your number is, right? Unless you're going to test to see if it makes sense. If you tell me what all those numbers are and find the SDT like this, I have complete confidence that I know you guys can plug it in and see. Everybody understand what I'm saying? If you tell me that you know what all these numbers are that you need, and you write it like this, you do it. figure out what it is. But if you're curious, in this case, to see if it doesn't make sense, so you plug that stuff in here. This is 2 times 20, 40 plus 2 times 100, 50 minus radical 2, that's 40, that's 50. Next was, minus radical 2, 100 times 40 over 2 times square root 4, 0, 0 minus 12,000. Okay. Any questions on that? So Mike, can you explain to me a little bit what would bother you? You think about circle problems, was there something you saw that was kind of disturbing you a little bit?
Yeah, I can't remember the exact comment. It was on your website, exam 1. For the second word,
Exam 1 from what?
2023. It's the ones you have listed at the very bottom.
Okay. My old 1060 exams, or the old calc exam, are also good sources. Just gotta pick through it a little bit, to find out what the appropriate problem. Problem about the sun is directly overhead at noon. But there's no, about 2 points take off in the same airport.
Yeah, I think I was, getting confused. Could you work on number 1? I don't remember.
Oh, the one about the sun and flash on. Okay, sure. Okay, so here's the problem. The sun is directly overhead, so I'll read this and we'll try to draw a picture of it. The sun is directly overhead at noon and sets at 6 p.m. This is kind of a circle problem away. You are observing the shadow of a 60-foot tall flagpole in the middle of a parking lot. How fast is the shadow of the flagpole lengthening right at 4 p.m.? Okay, so let's kind of capture this information here. Okay, so the sun is directly overhead at noon and sets at 6. You you're observing a 60-foot flagpole. You really want to get out one, but whatever. You're observing a 60-foot flagpole in the parking lot. And the question is, how fast is the shadow of the flagpole lengthening right at 4 p.m.? How fast? So let's take a look at this. So here's your flagpole, big parking lot. And we'll say the sun is over here. Now it casts a shadow. And here's the shadow. Everybody agrees my assessment of this is shadow. I can label 60 flagpole, because that doesn't change. The flagpole knows. What else, Charlotte? What's it? Maybe, never heard, of an age for hypotenuse. Well, what else has changed? There's something else that changes. Probably. Sun changes, new, by the way, how long do you expect the shadow to be right at now? Right, how long do you expect that, what should approach as you get closer and closer to sundown? Well, actually, more than that, right, I would expect, when the sun's almost flat, I would expect it to be almost infinite, right? There'd be, we're ignoring curvature of the earth or whatever, but as the sun flattens out, the shadows get longer and longer and longer. So, I think I'm gonna label this. Because that changes sunsets, right? When you're very, very close to noon, it's very, very close to power two, isn't it 90 degrees? And when you're very, very close to dinner time at 6 o'clock, this is getting very close to zero, right? Because that thing's like miles away, very flat. What's the sun information telling us? This is actually kind of, so let me kind of draw another diagram here, so it's short. And the sun. The angle the shadow makes should be exactly the angle the sun is above the horizon. Right? So what is this first piece of information? This is the hardest, I think this is the hardest part of the problem. What's this information? That information is going to tell us the change in theta. At noon, we'll say theta is power 2. At 6 p.m., what will we say theta is? So I would expect theta to change power 2 to 0. Oh. Are people getting bigger or smaller? Noon to 6 p.m. What's that in mind? That angle theta is it getting bigger or smaller? Smaller. So my dx is theta t minus power 12 radian. Okay. What's being asked? at 4 p.m. But somebody give me something better than 4 p.m. Right, I put this in the 4 o'clock. I put this in terms of something, one of the players. Good, good, right. So what angle is this going to be? So it's straight overhead. It's like 90 degrees at 12. It's all the way down to 0 at 6 o'clock. So 2/3 of the way of that, it should be down to what? Theta should be. That makes sense. So it should be pi/3. So it should be 90 at noon. It should be 60 at 2 o'clock, 30 at 4 o'clock, and 0. So. Okay. So. That's what we're looking for, the S and T. Looks like I need an equation balancing, S and theta. If I look at 60 over S, what is that in terms of theta? No, it's, there's no hypotenuse involved. Yeah. Good. Good. So. You don't have to take a step. I'll move the S over here. You know what I hate? I hate taking derivatives. So let's DDT this thing. That's a 0. Yes. T tangent theta plus S secant squared theta. Theta. Everybody see how I got that derivative? So let's see what we got going for us here. I know what theta is. I know what d theta t is. Power 12 radians per hour. Theta. I need to know what S is. But that's not a problem because this theta is pi over 6. That means the tangent theta is d over 61, right? Yes. And so S equals 60 over tangent theta, which is 60 square root. So let's see what it shows. The SPT, I don't know. It's okay. Tangent theta is 1 over right 3 plus S, which is 60. Secant squared of theta. Well, let's see, I guess cosine of theta is factor cosine squared is So it's. Uh, this is. Up here, yes, T. Oh. It's equal to, I think it's over the other side. It's positive. What right? T is. That multiply that back. I get S. T. A little over 60 feet per hour, but it's growing at that point. So that means, divide that by 60. That'll be how many feet per minute it is. So that velocity. This is about, well, this is equal to time over 3 minutes. So the lengthening of the shadow at that point is probably observable because it's growing about a foot a minute. Right, so like maybe an inch every 5 seconds, something like that. Probably see the shadow. By the way, this last step wasn't really necessary in the problem, but you know what it did is it made me look at it and say this is a reachable point. At 4 o'clock in the afternoon, the sun is 30 degrees above the horizon, to see the shadow growing at the rate of about an inch every 5 seconds. It's not completely. Okay. Any questions? Okay. So here's one. I will read this to you and write the relevant things up. A clock has a minute hand of length 8 inches and an hour hand of length 4 inches. How fast is the distance between the tip of the minute hand and the tip of the hour hand, changing at 1 p.m.? So let's pour some here. This was a terrible, there's one little trick bit in this. So it says, you have a clock. The minute hand. Eight inches. And hour hand is 4. How fast is distance between tip of minute hand and tip of hour? Change. I have one. So we have a old fashioned clock. Let's see how. Fast it changes. Here it is. Hour hand. Here is minute. That's a beautiful rendition. How should I label it? Help me doll this thing up. Those are two safe labels, but that doesn't change. Ultimately, just kind of looking ahead, what else should make me label on? What's it? Oh, that's a great idea. Yeah, let's do that. Sure. Yeah, because that's changing, that's somehow relevant. What else? Right, because it does eventually ask something about the distance between the tips, right? We'll call this an S. Now, my quest is. We want to find the STT, and when do we want to find the STT? I'm sorry. At 1 p.m. Agreed, at 1 p.m. But can we put that in terms of something of one of our players? It's the angle. 'Go ahead, you're done, say it. What's the angle between minute and hour? 90 degrees. That's what he's supposed to do. 30, 69, 1, 2, 3. Okay, what are y'all thinking about this? Because actually, looks like I'm gonna need something relating S and theta. I agree. This looks like a law of coincidence. So applied to our particular situation, I have S squared is 8 squared plus 4 squared minus 2 times 8 times 4 cosine theta. Let's see, that's going to be 80 minus 64. That should be the equation that we need to take care of this. Am I up here? Well, shoot, let's DDT. Yes. 80. By the way, let me ask you a question before we go further. What do you expect the answer to be? Do you expect the STT to be positive or negative? So at 1 o'clock, is the distance between tip of the minute and tip of the hour, are they getting closer together or further apart? Close together. So I would expect the S is back negative, right, because they speak. Let's see what happens here. What's the verb cosine? 64. Sine theta. Theta. And so what am I looking for? The SAT? Now. What do I need to know? I need to know S. I need to know theta. I need theta T. Well, theta, I've already kind of figured out, well, 1 o'clock theta has to be 30 degrees, opposite. And S squared is 80 minus 64 cosine, in this case, power 6. And the cosine of power 6 is yeah, it's radical field. So this is 80 minus 32 radical field. So S is whatever this unfolding mess is, square root of 80 minus 32. But I am missing theta T. There's actually one rather silly, subtle piece of information. Do we have a use this property? Do I know what it is? That's right. We have not used the fact that this is a clock, right? And so in a clock, I know how fast things turn. So in a clock, minute hand. Let's well, how fast does the minute hand spin? It goes all the way around in what amount of time? An hour. So all the way around is how many radians? 2 pi. In 1 hour. And how about the hour hand? Oh, yeah, good, that's right. It's not 24, it's 12, right? Hour hand goes 2 pi radians in 12 hours. So this is 2 pi radians per hour. And this is pi over 6 radians. So, what about the single? Think about it this way. The hour hand is running, but it's running slower than the minute, right? So you theta dt, speed of the hour hand is pi over 6 radians per hour minus 2 pi radians per hour. And that's going to be minus 11 pi over 6 radians per hour. That's right. You expect there to be a negative, right? So think of it this way. To get how much, so what's happening is this is going this way and this is going this way faster. So if you want to measure the change in that angle, it's this rate minus this.
But once the minute hand passes the hour hand, then it can like d theta over dt switch to volts.
No, because the way we measured it, no, it wouldn't switch at all, because what happens is now when it's passed, we're measuring from the hour hand back, so now you've got this complete circle, it's still negative. Right, because the way we're doing is we're measuring from the hour hand back to the minute. So once it passes, then it's got almost 2 pi, but it's always something. Right, it's sort of like, well, maybe it's never happened to you, but it's certainly happened to me. You ever been lapped running on a track? Yeah, that's kind of what happens. It's minute increments, right? And the relative speed is all the same, it's just minute. Right. Good question.
Does that mean it's always gonna be negative as the which is
Well, so the way we set this up is we're measuring basically the rate of speed of the hour and minus the rate of speed of this. And so what happens is as it catches up, you've got a negative because the angle's closing, then the angle's 0. And when it moves on, now when you measure the hour hand minus minute, hand, you've got like an entire circle. So we like that. So let's see what happens here. I think I've got everything we need to plug this in. This is, right, so S was, I'm just gonna call it S. Is equal to 32 sine pi over 6 times the theta dt, which is minus 11 pi over 6 radians per hour. So the SDT, which change in distance, is sine of pi over 6 is 1 half. So this is 16 times minus 11 pi over 6. Over S. The whole. And so I'll give you kind of a final answer here. So this is going to be minus 88 3 times S, whatever S was. Right. Whatever this comes out. Each one out. And if you divide that by, say, 60, you get inches per minute, which all sense. Yes, yeah, that number seems about right. Okay, any questions? here's one. You got, this is kind of one that's a little bit of a challenge. So I have, I've got a couple of coal cars are connected by a 39-foot road. A 39-foot road. Um, and this road passes through a pulley 12 feet over the track. 12 feet over the track. Q is the point on the track directly below the pulley. And cart A is being pulled at 2 feet per second away from Q. Feet per second away from Q. How fast is cart B moving toward Q? When cart A is 5 feet. Wow, that's a mountain. Okay, again, I think this is definitely one where we can. Okay, so we've got a couple of coal cars set on the track. And remember, this doesn't have to, it's just to help. Got part A. And it's connected by a pulley. Oh, and it said something like Q is the point directly under. Now you all can imagine this, right? So you got two coal cars up here in an Indiana Jones movie or something. They're connected by some rope. And you pull one. If you pull A, it's gonna pull B. Agree? It goes up to that pulley and it's gonna drag B along. Okay. And I wanna know how these interact. Okay. There is just, this is a very incomplete picture. What else should I be like? Okay, right. This dotted line is always 12. No changing that. Correct? What else? Okay. I'm gonna call this distance from A to Q. I'm gonna call this little a. I'm gonna call this little b. Little a signifies this the distance of card A, little b signifies it's here. And you know what? This is part of my road, so I'm thinking I'll be labeling this too. I don't think. But I remember Eli, one of our and our problem that we did earlier with shadow, you said to label the hypotenuse, and we never did use that, but it didn't hurt us none, did it? Right, so if I've overlaid, I've overlaid. Okay, let's see. Carts A and B are connected by a 39-foot road. This is gonna be important. Anybody tell me how can I take that statement and interpret it in terms of what I've got? Perfect. Good, good job. This rope passes through a pulley 12 feet up. Yeah, I think I got that covered. Q is the point on the track directly beneath the pulley. Got that covered in the picture too. Okay, cart A is being pulled at 2 feet per second away from Q. What's that? Good. There's a lot more variables than we had before, but we shall persevere. How fast is cart B moving toward Q when cart A is 5 feet? Okay, so this is. Yeah. Okay, so what are we looking for? What is our quest? Agreed. When, what's the? Good. And I think we've led this about right, but let me ask you this. In our answer, what do you expect to be true about the VDT? I agree. It's gotta be negative, right? I mean, if I'm gonna pull A toward me, then B better be decreased. I would also expect it to be somewhere near this, right? I would expect to pull this 2 feet per second and have this go 200 miles an hour. Right? Do I agree with that? So let's see if we get an answer that is reasonable. Okay, so what do we got here? We know some crap about X and Y, the ADT. And we're looking for the VDT, when A is 5. So, suggestions. That's going to be a crucial piece we need later, but the good, as long as something in your problem can change, don't plug in the number 4 too soon, and get burned on. See if I see any equations. Okay, so which Pythagoras theorem means? Is oops, right? A squared, let's try this again, A squared plus 144 is equal to X squared, right? Why did you pick that side instead of the other one? Okay, yeah. Okay, good. Let's think good. I'm gonna put the other, we got the other side too, right? Let's DDT. Remember this. There's a similar one here. So I have this. Huge mess. Let me take this two off. And I also have B. Right here. What was our quest? What are we looking for? Yeah. Okay. But I know about zilch. I don't know what the line is. Huh. Let me ask you this. Anybody tell me how I figure out what step is? All right, because I'm gonna need B. Don't got it. This is why. I don't know. What's the relative time? I don't know anything about B, but I do know about A. What's A supposed to be in a relative time? What's X? But if X is 13, I can figure out something else. What's that? X plus Y is 30. So Y is 6. And this allows me to get B because B is, well, B squared plus 144 is 26 squared, which I believe is 676. So B squared is 532. B is around 532. Okay, got that. Check that off my bucket list. What is Y? Well, we found it along the way, didn't we? How about them apples? Well, what about IDT? Pythagoras theorem. Because if A is 5, then X squared is 169. So that means that X is 13. You okay that part?
Yeah.
And once I know that X is 13, then I know that Y is. Right, this is, there's a lot of pieces to this. Okay, so I've got B, I've got Y. See, Y to T is a mystery. Here's kind of a hint though. I've got this stuff about the A to T and A that I haven't really used. I use A to find B. Let's look at this equation right here. What do I know in this equation? I know A, I know d/t, and I know x, don't I? So a is 5. d/t is what, 2? X is 13, and so dx/dt, well, 10/13. But I don't need dx/dt, I need dy/dt. That's sort of, right? However much you're pulling in, you're making y shorter, right? And that's a little bit of iffy with this. You'll love the calculus, it's scary. What happens if you keep this? If the x to t plus y to t 0. And this is exactly the physical observation you made, that the y dt t minus dx. Everybody agree with me? So y dt is negative 10/13. So how fast is the cart moving toward the middle point? Y is 26. Y dt is minus 10/13. And B is radical 5/32. So this is negative 20 of radical 5/32, and that's so. So this would be like a little bit less than a foot per second. Let's get closer to this ballpark. This seems about right. Everybody okay with that? Okay, is everybody gonna be able to make a review session tonight or this afternoon? I will be out of my office, but I should be back in about 2:30. I'll be here obviously for the review session then. Look over some problems. That will hit that hard and